Hi everyone, welcome to the introduction to Vivado Design Suite and the PYNQ Z2 Development Board that we'll be using for our digital design lab. So we know that Vivado Design Suite is a software suite developed by Xilinx for designing and programming of Xilinx FPGAs or system on chips, that's SoCs. So it is this suite which provides a set of tools and features that would support our entire development flow, right away from designing, that means giving the design entry, simulating the hardware, and it will also help us in synthesizing and implementing the design on an actual Xilinx device. So it is in this suite that we will be entering our description in the form of hardware description language, and we'll be using Verilog for this lab. The board that we will be using in this lab is the PYNQ Z2 Development Board. So PYNQ essentially stands for Python Productivity for Zinc. That's the Zinc family of boards, and PYNQ Z2 board is specifically built to support PYNQ and is suitable for a wide range of applications. More about the PYNQ Z2 board a little later. So the first step you need to do for this lab is to install Vivado Design Suite on your systems. You may have to first log into AMD, then download the suite. You could take a 2018.3 version or a later version. So you may want to take an earlier version if you wish, but please be prepared that you may have to make some space for this installation. The second step after this installation is complete is to download the board file and the master XTC file for PYNQ board from this particular link. They'll be downloaded in the form of a zip file, so you can download and keep them, and then we'll use them when we need them. So note that what we have done in step 1 is just install Vivado, and in the second step we are trying to find the files which will help us integrate the PYNQ board with Vivado. So on this link, PYNQ Z2 is selected. You download the user manual for your reference also, and download this board file and this master XTC file. So what is this board file and XTC file? So board files essentially describe the properties, the physical properties and configuration of the board we're using. So we need this description and configuration for the PYNQ board, so that the Vivado suite knows that when we enter a design description, how it has to be connected to the FPGA board. And it also includes information about the FPGA, what are the connectors or levels or other input and output pins that we'll be using on the FPGA, so all the hardware specific details. And these board files are provided by the manufacturer. The XTC file, that means the Xilinx design constraints file, this contains the constraints and settings of your FPGA design. So when we'll open a project, right, we will see certain options like adding sources, adding constraints. So this constraint file will come in handy at that point. And in this XTC file, when we will create a project, you will see that in the first example, we will actually define what are the input and output pins of the board that we'll be using. In the next step, once the installation is complete and the board files have been downloaded, we want these board files to be read when we open Vivado. So suppose if you install the 2018.3 version, on the C drive you will see this particular path. So please go to C drive, open the Xilinx folder, go to Vivado, go to the version, then open the data folder, and within data go to boards. And within boards, if you don't see a folder called board files, just create a folder. So all the contents from the folder of board files which you downloaded for PYNQ Z2, please extract them, copy them and paste them onto this folder. Alright, so I have extracted that PYNQ board file folder. I copy them and I need to paste this into the board files folder. So I go to C drive, Xilinx, Vivado, into the version data, and here I'll look for boards, and I don't have a folder called board file, so I'll just create one. and I'll paste those board files here. These board files are for PYNQ Z2. So we open Vivado, and the first thing we will do is create a new project. So when you click on create project, go next, you can give name of a project, and I have also given a project location. There will be a separate subdirectory created for this project like this. So I'm going ahead. Next. Note that the type of project is RTL. Now RTL is a type of abstraction level for digital circuits. So we'll talk about RTL a little bit more in class perhaps, but know that all the projects, all the experiments that we'll be doing in this lab will be RTL projects. Next is to import the board. What is the default part that we are choosing? So instead of part, you could have done this by part number also, but we will click on boards, and if you have already copy pasted those board files and you have refreshed this once you write in the search PYNQ Z2, this should appear. Now normally what would happen is the first time you copy paste it, and suppose you open Vivado and it does not appear, it will be a good idea to refresh this once, and for the very first time this starts appearing, but this may not be selectable. You will see a download button, an install button here, like this one. You will see a similar one here. You install it first, install the board files, and then next time when onwards this will be selected. Okay, so you install it once and then you select it, proceed to next and finish. Okay. Note that at the beginning we did not create any sources. In any Vivado project we will have a bunch of sources. One is a design source. This is essentially your Verilog code. This is the description of the circuit. So this is the source of the design. Next are constraints. Constraints will also have sources. This is where your XDC file will come into picture. Okay. And the third is the simulation source. So simulation source essentially helps us at the time of running a simulation. It will help us give certain stimulus to the circuit, and for what inputs should this circuit be run, so that whether it's working correctly or not, that can be checked. So to start, let us start with the design source. We don't have any design source selected right now, so I'm going to right click, add source, and add or create a design source. So I'm going to create a new file. The language which is selected is Verilog. I'm going to call it half_adder. Save it in the local project file, project subdirectory itself. Okay, finish. Note that here input-output port definition can be given here, but we are not selecting it right now. We will write all this in the code directly. So I'm just going to go ahead and say okay. You see it's updating here. And one design source called half_adder.v has been created. If I double click on this, you can see that this is simply the module for half-adder. So let us quickly write this. We are creating this circuit for a half-adder. So A and B are our input ports, and sum and carry are our output ports. I'm going to define A and B as input and sum and carry as the output. And now comes the assign statement. So assign to variable S. Sum is XOR of A and B. So A XOR B. And to carry, we assign A and B. There are semicolons everywhere. This module is complete, so I'll just save it. Now, while the design source is ready, the constraints, which mean which pins of the PYNQ board we will be using here, those things we haven't really taken into consideration. Note that you can go and run the simulation, of course, but you cannot connect it to the PYNQ board unless you have added the XDC file. So for now, let us just run this simulation and see. Okay, so we haven't connected the constraint yet, but let us just run the simulation and see. Run behavioral simulation. So it is just compiling. There's no error in the code, and you know already that the output of the simulation is shown in the form of a timing diagram. So this is that timing diagram. Okay, by default it is run for 1000 nanoseconds. That is a default time. You can zoom in or zoom out, and you can see, if we make it a little bigger, this is the timing diagram. Right now we have not set any values for A and B, the inputs. That is why there are no output values shown. Here what we can do is we can force a certain value on A and B and just check something very quickly. And now you should add the source of constraint. If you recall, constraint files are those files which are specific to a particular board, and for all the input output configurations, the pin numbers and many other parameters that you may want to connect between your ports, the ports that you have defined in your code, and to the actual board, that is what is defined through these constraint files. So add or create constraints, select this, and next we are going to not create a new file. We already have a constraint file for PYNQ which we had downloaded and extracted and kept. I'm just going to add that file here. Okay, so we go to that particular folder, select this. So go to the location where you had extracted that XDC file, select it and say OK, finish. So now it shows me that there is a constraint file selected. Okay, what to do in this constraint file is what we will see next. So when you double click on the XDC file, you see a bunch of description about various switches, LEDs, the RGB LEDs, the actual LEDs, buttons, all these things. These are all components on the PYNQ Z2 board. Okay, so to understand this better, let us take a look at the PYNQ board. So this is the PYNQ Z2 board. For the scope of this experiment, what is important to us are these things. At the bottom, you can see that there are two dip switches. Dip switches basically mean you can just change the state by toggling their position. Okay. So we have two dip switches here and 4 buttons and 4 LEDs here. If you can see, LD0, LD1, LD2, LD3. Okay, and there are 4 buttons also. BTN0, BTN1, BTN2, BTN3. So what we plan to do in this experiment of half adder is that we can actually program these two to be inputs, or we can also program any of these four buttons to be the inputs. These buttons are press type, so if you're holding them down, its value is 1. If you leave it, the value is gone. Okay. So suppose we have decided to give A and B to these switches and let them both be in 0 state to start with, and I want to give A to SW1 and B to SW0. Okay, so these two settings have to be included in the XDC file, and for displaying the output for the scope of this experiment, let us just say that we want the LEDs to glow to show whether the output is high or low. So suppose I assign this LD1 to my output port C, which is carry, and I show sum on this LD0. Okay, so whether or not these LEDs glow will show us whether output is high or not. So I'm going to connect LD1 to carry and LD0 to sum. Now that we have decided this, this would be a good time to look at the user manual of the PYNQ board, which we had downloaded initially, and we will come back to this when we are loading the bit stream onto this. So this is where we open the user manual for PYNQ Z2, and we will jump right away onto these LEDs, buttons and switches. Okay, this is where the various ports will be defined. So this is what I was talking about. We have decided to give inputs to these dip switches and show the output on these last two LEDs. Okay. So we need the names of the programmable logic pins corresponding to these options. So we are not using push buttons this time, we are using switches, and so the PL number, pin numbers are M20 and M19. Okay, so if I go back to my constraint file and look at the switches, that means these two, I need to firstly uncomment it, and M20 and M19 and M20, so that is correct. We had decided to put A in SW1 and B in SW0, right? So M19 one has to be the port, the input port should be renamed as A, and M20 should be renamed as B. We go back here. So this portion, the argument, what is written here is SW1, this should become A and this should become B. So it's important to look at these programmable logic pin numbers from the user manual so that we don't make a mistake. So this one was corresponding to switch 1 and this was switch 0. Next is to define outputs, and for outputs we will go to LEDs. So now here there are a bunch of pins. We don't know which one is corresponding to LD1 and LD0. We'll again go back to the manual and look at this description. So we decided to use these two, right? And we said we will put carry in LED1 and sum in LED0. So carry in P14, these two firstly, carry in P14, port C, and sum in R14. Okay, this is all we need to do in the first experiment of half adder. This is how we want inputs and output ports to be defined. Once this is ready, we'll just save this file, and we are not going to disturb anything else. Okay. We have already run the simulation and looked at the timing diagrams. It was working just fine. And now what we can do is we can look at the open elaborated design, or we can run each of these steps individually. If we actually run bitstream, it is going to run all these steps individually, but for now let us run them one by one. So I'm going to go to synthesis and run synthesis. You can see that it's running. So this could take a few seconds or maybe a minute. So it says run implementation. I'm going to go ahead and say OK. Run the implementation as well. So it is now initializing the design and running the implementation. So implementation has been completed. I can open the implemented design now. And this is how the implemented design looks like. So if you actually zoom into, say, suppose I select a particular area and we zoom in much further in, you can see it's proposing an implementation with flip-flops. So we will, this is not relevant to us right now, but we will come back to it when we discuss this more. So implementation right now, this is how it looks like, and we could have actually also looked at the schematic. And this is how the schematic looks like. So A and B are the two input ports, C and S as the output, and this is what is expected. So once the synthesis and implementation have been run, now is the time to generate a bit stream. And then once the bit stream is generated, it will be loaded onto our PYNQ board. So we click on generate bit stream and we say OK. So the bit stream is ready. It has been generated. We could view the reports, but what we want to do is now to load this bit stream into the PYNQ board. So we will open the hardware manager. And right now you can see on top, no target hardware is open. This is because I have not connected my PYNQ board to my system yet. So there is a USB cable. I'm just going to use my laptop to power this. So I have connected the PYNQ board, and at this point, if I press on open target and say auto connect, it now shows me the option of my board, which is already selected. So we will now click on program device, and it will show us the link of this bit stream, half-adder.bit. In case you are not able to see this link, you will have to manually go to this folder, the project folder, and follow this sub path and find the file which has a .bit extension and then insert that link here, that path here. And I'm going to click on program. So now my bit stream is being loaded onto the PYNQ board. So to test, now everything is done from our side on Vivado. Let us now go and see how this looks like on PYNQ. We programmed this device and loaded the bit stream onto this. So now this is ready to use, and these are A and B, right? So if I make A as high, sum should be 1. So we can see that this LED is glowing, right? And ideally what should happen if the other one is high and this one is low? Suppose this is 0 and this is 1. Again, sum should be 1 and carry should be 0. That is what is being observed here. And when both are 1, we should see that sum is 0 and carry should be 1. So if I make both as 1, you can see that this LED is off. So sum is 0 and carry is 1. So while that is the end of the implementation and testing on the FPGA board, now would be a good time to look at how simulation can be done using test benches. So note that in the earlier case, at the stage of simulation, we would simply force a value of a variable, right? But that may not be a very helpful methodology always. In order to create a test bench where we can specify in advance all possible combinations of the inputs that should be taken during simulation and for whom output should be displayed, that is another way of adding a simulation source. So note that in earlier we had only one simulation source, sim1, which just had the half adder file. Now what we will do is I'm creating another simulation source called sim2, and in this simulation source I'm going to create a test bench. So let me call it HA underscore test bench. And again, I'm not specifying input output ports. I'll do that in the code. So once this is created, you notice that now there's a sim2 source and we still see HA test bench and half adder. So I'm going to double click on the test bench file and now write the code for this test bench. So we've already discussed the test bench code in class. This is how it looks like. Now one of the things I would do is right click and make the sim2 source active. And the second thing to do would be to make this test bench the top module, because the test bench is calling the half adder module. So that makes the half adder module, that is the device under test, to be the lower order module, and HA, the test bench for this half adder, should be set as the top module. Once we do that, and you actually click on it, and you should be able to see the sub module HA1 that has been created. Now when you run the simulation, so you can run the simulation for a particular simulation source. So to start with, let us just right click and reset the simulation and then start the behavioral simulation again for just sim2. Now when you look at the timing diagram, you can see on the screen that based on our specification, for every 10 seconds, the combinations of A and B are put up and corresponding values of carry and sum are also displayed.